Welcome to this video cast on standard reduction potentials and using them as a predictor of certain reactions. Make sure that you've got a periodic table out in front of you. You've got some paper and a pencil so you can take notes. If you don't have paper and a pencil in front of you right now, get some out, pause the video now, make sure that you can write down some things and have a copy of this in front of you as well. Thus far in our discussion, we've talked and used the tabulation of standard reduction potentials to examine things called voltaic or galvanic cells. We've used these values right here to understand aqueous reaction chemistry. Today what we're going to do is we're going to take and use these standard reduction potentials to help us make predictions, not about the amount of electromagnetic force or a voltage that's produced by a reaction, but whether or not a single replacement reaction or other redox reaction will occur. And so in effect, we're going to answer the question, reaction or not, during this video cast. And so it's called single replacement reactions and other types of redox reactions using electrochem as a predictor. So far we've looked at a tabulation of the potential or the possibility that something will be oxidized or reduced. And just as a quick review, remember that when something is oxidized, it goes up in charge. So for example, silver going to silver +1 would be something that is oxidized. It's going up in charge from 0 to +1. Reduction is reduced in charge or going down in charge. And you can remember oxidation means up in charge because they both start with vowels, and reduction meaning down in charge because they both start with consonants. And this would be the opposite, of course, if we had Ag plus going to Ag0. Usually you don't write the little 0 up here, remember. That would be going down in charge or being reduced. Now, scientists have tabulated or made a table of the possibility, or another fancy name for possibility is potential, of lots of things being reduced. They just picked reduction as kind of the thing that they want to tabulate. This is called the table of standard reduction potentials, and it's this yellow table that we've got on the periodic table. The things way up here at the top have really high standard reduction potential, and so those are going to undergo reduction. They're going to be reduced or lowered in charge. Things way down here at the bottom have a very negative reduction potential, meaning that they're most likely going to be oxidized. These things will be reduced. These things will be most likely oxidized. And we can actually talk in terms of strength or the ability to become reduced or the ability to become oxidized. And there are some fancy terms that we use to describe this we'll just talk about in just a second. So these standard reduction potential tables can tell us which is more likely to happen. Is it more likely that manganese +2 will gain 2 electrons and become manganese, 0 charge, remember? Or is it more likely that cadmium +2 will gain 2 electrons and become cadmium of a 0 charge? Which one is more likely to gain electrons and therefore be reduced in charge? We can look on this chart and we can find out who's more likely to be reduced. So the two once again are manganese and cadmium. Manganese and cadmium. Let's find those two on the chart right here. And if you look down towards the middle of the chart or so, you'll find manganese right here, and it has a standard reduction potential of gaining 2 electrons of -1.81. And then the second one, remember, is cadmium. Whoops, that's a little bit too zoomed in, but we'll find cadmium on here too. Cadmium is just above it a little ways right here. Can you see it? Cadmium +2 gaining 2 electrons become cadmium solid, and its standard reduction potential is -0.4. So let me write those down on the piece of paper again. Manganese's Manganese's potential is negative 1.18. Cadmium's is negative 0.40. Who is more positive? Who is more of a positive value? This tells you which is more likely to be reduced. Because remember, the higher the number on here, or the more positive the number, the more possible, the fancy word they use is, which has more potential to be reduced. Well, obviously this guy's more positive than this guy, and so cadmium's reaction is more possible than manganese. And if we actually had a reaction occurring where we had cadmium positive 2 and cadmium 0 and manganese 0 and manganese positive 2 in a galvanic cell setup, cadmium would be the thing that is reduced, and therefore it would be the cathode of the reaction. And manganese would be the thing that's oxidized, and actually the reaction would run in reverse for manganese. This chart helps us determine that, and you need to become good at looking at this chart and determining which thing will happen. So we can also use the chart to help us determine the opposite. Which is more likely to happen? Cadmium becoming cadmium plus 2, or manganese becoming manganese plus 2. Now remember, this is just the backwards of these reactions, and so this is called oxidation. Okay? Now remember, we said that things on this chart that are at the top have the most possibility of being reduced. Things at the bottom have the most possibility of being oxidized. And you can still see on here that I have the 2 marked. Here's cadmium, and then here's manganese right here. And you can see that the one that's lowest on the chart, or the most negative, the one that has the most possibility of being oxidized, is manganese. And so to answer this question, which is the most likely to happen? Well, this one is the most likely to happen because it has a negative 1.8 reduction potential. Now, scientists could have taken this entire chart and turned it around and made it be upside down. And they could have called it an oxidation potential chart. But they didn't. They call it a reduction potential chart. And so you need to get over that, even though you probably want an oxidation potential chart. And you need to be okay with everybody in the world talking in terms of a reduction potential chart. Well, let's move on from here and let's talk a little bit about what this will allow us to do. What this allows us to do. We can use the standard reduction potential table to answer the question, reaction or not. You can use it to help answer the question, reaction or not. So, for example, here is a redox reaction. Let me zoom out just a little bit so you can see the whole thing. Silver nitrate, aqueous, is put in contact with some magnesium solid. And if this reaction occurs, it would become magnesium nitrate and silver. Silver of a 0 charge right here, and then of course magnesium would become a charge, and the nitrate would just be a spectator. So to know what's happening in here, since it's a redox reaction, we should assign oxidation numbers. And of course silver right here is in a +1 state. The nitrate is in a -1 state. We could go through and assign nitrate a +5 and oxygen -2, but let's not do that. Let's just keep nitrate as -1. Magnesium over here is 0. And then over here on the right-hand side, magnesium would become +2. Nitrate, of course, would still be its -1 charge. And then silver would become 0. And so we could tabulate this and say that silver is going from silver +1 to silver 0, and therefore it's reduced. And magnesium is going from magnesium 0 to magnesium +2, and so it's being oxidized. Okay, once again, silver's being reduced, magnesium is being oxidized. Now, we want to answer the question, reaction or not. We, of course, can write the reaction on paper, but we're using it as a predictor. If we actually did this, would the reaction occur? Would silver be reduced? Would magnesium be oxidized? Well, remember what we just showed? Here's our chart that can tell us whether or not things can be reduced very easily or things can be oxidized very easily. And we need to find these two critters on there, silver and magnesium. I'm going to zoom in right here, and we'll see if we can find them. Okay. We found manganese here, but now we need to find magnesium. Here's magnesium. It has a standard reduction potential of negative 2.37. So let's write that in here. Negative 2.37. I'll zoom out in just a second again. But I'll slide this down, and we'll find silver right up here. And silver's standard reduction potential is 0.8. 0.8. Positive 0.8. Okay? Zooming back out now. Positive 0.8 here for silver. Negative 2.37. Well, who has the better possibility of being reduced? Well, you can see that silver's way up here, and so its reduction possibility or potential is way greater. Is silver being reduced in this written reaction? Sure it is. It's going from +1 to 0. And since it has a more positive reduction potential, that's what silver wants to do. Is magnesium being oxidized? You bet. And remember, magnesium is way lower on the chart than silver. And so magnesium has a much more potential to be oxidized than what silver has. Will this happen? The answer is yes. The answer is yes. So you always got a 50-50 chance, reaction or not. But, here's some math to back it up. Not necessarily math, just bigger or smaller numbers to back it up. Now, before we go and do a whole bunch of these reaction or not predictions, I want to go through a little bit of fancy terminology, because every once in a while you'll see some fancy terminology on the AP test or in a book, and you'll be like, oh, we never really talked about the fancy words that mean exactly the same thing as what we talked about. Okay? If it's reduced, it's also known as an oxidizing agent. If it's reduced, if the thing is reduced, oops, that's not supposed to be there. If it is reduced, it is an oxidizing agent, okay? You can think of it as it has the possibility of going out and causing oxidation to something, kind of like a secret agent goes out and does things to other people. If it's oxidized, it's called a reducing agent, okay? If it's oxidized, it's called a reducing agent because it causes other things to be reduced. Well, look at the strength of these abilities on the periodic table chart. Okay? Look at the strength of these abilities on the periodic table chart. Here's the chart once again. Remember, these things have the possibility of being reduced a lot. And remember, oxidation and reduction always happen in a pair. And so if one thing is reduced, that means another thing has to be oxidized. And so we call these things not only having a good possibility of being reduced, but being very good oxidizing agents. And these guys down here having a good, strong possibility of being oxidized, these are good reducing agents, real good reducing agents. And you can see up here, this is actually a historical note, but you'll notice oxygen right here, O2, is listed towards the top of things that have the potential to be reduced. That's because it is a good oxidizing agent. And that's what originally, a long time ago, people only understood, is that oxygen was an oxidizer. It oxidized other things. When it was doing that, of course, it itself was reduced. It itself was reduced. So back to the questions again. Reaction or not. Now that we know a little more fancy terminology and we've done one of these, here's a whole bunch that we're going to go back to the prediction question, reaction or not. Here's a whole bunch of these examples now. And you can pause the video along the way and see if you can do the predicting along it too. So here's another single replacement reaction, cobalt plus aluminum chloride. If this reaction were to occur, what products would be produced? Well, cobalt would become cobalt plus something, okay, a positive something, probably +2, maybe +3. You're not sure of the charge. But you know what? You've got a list of a bunch of these on here, and you could find cobalt on there. And then aluminum, it would go together with the chlorine, of course, and the chlorine's negative. And then aluminum would go off by itself, and it would become aluminum solid of a 0 charge, okay? Now, let's take a look at a cobalt. Let's see if it's on here. Here's cobalt. It's cobalt plus 2 electrons goes to cobalt. It's got a standard reduction potential of negative 0.28. I'll just write that up here so then we can remember that. But cobalt goes to cobalt plus 2, so when we wrote this, when we'd write this, it'd end up being CoCl2. So if I assign oxidation numbers to it, like I did before, cobalt has a 0 charge here. Cobalt has a positive 2 charge here. Aluminum a positive 3 charge here. Aluminum has a 0 charge over here. And the chlorine is a spectator. That's a -1 here and a -1 here as well. Now the reaction isn't balanced, and I could go through and I could balance it. But what I really want to know is is it going to be a reaction or not? What's happening to cobalt? Cobalt's going from 0 to plus 2. Cobalt is being oxidized. What's happening to aluminum? It goes from plus 3 to 0. Aluminum is being reduced. To decide whether or not cobalt can be a reducing agent for aluminum, let's look at the chart. Remember I said right here, I pointed out cobalt. Maybe you can't see it because I'm zoomed pretty far out. But here's cobalt. Cobalt plus 2 electrons go to cobalt solid. It's negative 0.28. And then let's find aluminum on here. Aluminum is right down here. Here's aluminum posi 3 going to aluminum solid. It's negative 1.66. So zooming back out, negative 1.66 for aluminum. Who has the higher standard reduction potential? Standard reduction potential. Okay, here's cobalt. It's more positive than aluminum. Is cobalt being reduced in this possible reaction? No. Cobalt's being oxidized, right? So the answer to this one is no. The reaction cannot occur because cobalt cannot be a good enough reducing agent, or conversely, aluminum isn't a good enough oxidizing agent to cause cobalt to be oxidized, or conversely, aluminum to be reduced. This is the power of the standard reduction potentials, is it allows us to decide before we actually do the reaction, is it going to happen or not? Let's do another one. Magnesium sulfate plus nickel. Okay? Potentially, what would happen? Well, magnesium would go off by itself and become magnesium by 0, and this would become nickel sulfate over here. Assign oxidation numbers. Magnesium is positive 2 over here. It's 0 here. Nickel's 0 here. It's positive 2 here. Sulfate's a spectator. So we've got magnesium going from plus 2 to 0. Nickel going from 0 to plus 2. Let's look those up. Okay, magnesium we did down here before. That's in the box. It's negative 2.37. Magnesium is negative 2.37 for its potential to be reduced. What's happening to magnesium, by the way, here? Is it being reduced or is it being oxidized? It goes from plus 2 to 0, so it's going down in charge, right? So it is being reduced, okay? Nickel, on the other hand, let's look that up. I think have we looked at nickel before? Let's find nickel on here. Nickel is right here, right above cobalt, and nickel's standard reduction potential is negative 0.25. Negative 0.25. Okay, what's happening to nickel? It's going from 0 to positive 2. So nickel is being oxidized, and magnesium here is being reduced. What do the standard reduction potentials say? Remember, the one that's the most positive would have to be reduced. Is magnesium the most positive? No. So is this reaction going to happen? No. This one doesn't happen either. All right, now this next one, I want you to try. Pause the video now and see if you can predict whether this reaction will happen. Go through, assign the oxidation numbers. Go through and assign the oxidation numbers. Predict what the reaction would be. Look at this sheet and see whether or not you think the reaction will happen. And then play the video. Pause it now. Okay, in this one, chromium would go together with bromine, and it would probably become chromium bromide, probably 3, because chromium likes plus 3. Strontium would go over here, and it would be 0. Assigning charges, it goes from positive 2 to 0. Chromium's 0 here to positive 3. looking on the chart, strontium's way down here at the bottom. Okay, way down here at the bottom, it is negative 2.89. Okay, negative 2.89. And then chromium is right here, is negative 0.74. Negative 0.74. Okay, now what's happening to each? Strontium is going from +2 to 0. +2 to 0. And so it is being reduced. Chromium is going from 0 to +3, so it's being oxidized. Okay? Remember, to make this happen, to make this occur, what we have to have is the thing that has the more positive number has to be reduced. Is this more positive than this? Yeah, it looks like it, right? Well, wait a minute, I'm sorry. This is being oxidized, right? The thing that is being reduced, right here, going from +2 to 0, has to be more positive. I was pointing to the wrong thing. The thing that's being reduced has to be more positive than the thing that's being oxidized. Is this more positive than this one? No, it's not. And so, no, this reaction can't happen. This reaction can't happen because this one is not more positive than this one. Let's take a look at another one. This is an interesting one because it involves anions. Chlorine here would replace iodine, and we'd end up with KCl and some I2. Assigning oxidation numbers, chlorine would be 0 here, -1 here. Iodine, -1 here to 0. Who's being oxidized and who's being reduced? Chlorine goes from 0 to -1, and so it undergoes reduction. Iodine goes from -1 to 0, and so it is being oxidized. It's going up in charge from -1 to 0. Now, are the standard reduction potentials for these on there? Sure. Chlorine going from 0 to -1, right here at the top. Chlorine, 1.36, right up here. 1.36, okay? And iodine right here, going from -1 to 0. That's on here too. Iodine right here is 0.53. 0.53. Okay? So what's happening in this one is chlorine is being reduced from 0 to -1. Iodine is being oxidized from -1 to 0. Who has the higher reduction potential value? Well, obviously 1.36 is larger. And is that the thing that on paper is being reduced? Yes, it is. So this one is a yes. The reaction will happen. Okay, let's take a look at the next one. This is another one where I want you to pause the video and see if you can do it. Pause the video now and see if you can do it. Actually, I'm going to give you 2. I'm going to give you 2 right now. And pause the video now and write down both of these, have your periodic table out, and see if you can predict whether these will happen. One of them is a cation replacement. This one's another anion replacement. And see if you can make them happen. Okay, this one would be PbClO3, 2, and it would make copper. I'll do both of them at the same time. This one would make barium bromide and some iodine off by itself. Lead here is 0. Here it's +2. Copper is +2 to 0. Therefore, lead is being oxidized and copper is being reduced. Iodine here is -1. Bromine is 0. Over here, bromine is -1 and iodine is 0. So iodine right here, bromine right here went down in charge, so it was reduced. And iodine right here went up in charge, so it was oxidized. Now I need to look up and see whether these are possible. All right, let's find lead. negative 0.13. Let's find copper, and this is copper plus 2 now. Copper plus 2 going to copper solid. Be careful, there's a copper going to copper plus 1 as well. 0.34. Positive 0.34. Is copper the thing that's being reduced? Yes. And it has the higher standard reduction potential. So yes, this reaction will occur. Okay, now let's look at the iodine reaction. We looked at that one before. Here's iodine, 0.53. Positive. Bromine, right up here, 1.07. Positive. Okay, who's being reduced? This guy. Does it have the larger number? Yes. So yes, this reaction will occur. It has the higher standard reduction potential. So hopefully from this, you learned how you can use the standard reduction potential page, and you got a little bit more used to using it, and use it to help you make predictions. In this case, we used it to help make predictions mostly about single replacement reactions, but we used these standard reduction potentials as predictors of whether or not a reaction will occur. Good luck with your single replacement reactions electrochem as a predictor problems.